Swayam Prabha. Digital India. Educated India.
Hi and hello everyone. What we are seeing are queuing networks, and in which, just recall from the previous lecture what we have been doing. We considered a 2 queue or 2 node queuing network, right, 2 node, which is connected serially as given here, and it is something like the first node was MM1, and from which the input went to the second node, and that node has a single server with exponentially distributed service time with single server, right. So, in this, now if this is the system as we call, which is a network of queues or queuing network, is a 2 node network series which is connected in series one after the other. When the system state is represented by a CTMC on the state space and with appropriate conditions, right. This is the balance equation which gives a solution or which solves to this, and what we observe here is that the steady state system size probability of seeing n1 in node 1 and n2 in node 2 is simply equal to this quantity, which you can write it as in a way as P of n1 into P of n2, where this P of n2, right. Okay, so this is what we are observing, and this means that the joint distribution of the number in the system, in the whole system, we mean both the networks put together, is equal to the product of their individual marginal distributions, right. That is what we observed, and that, what does that mean? That means that the second node which happens here is also an MM1 queue which is independent of the first one, right. So, this dot can becomes M, that is how it becomes, okay. That is what, if it happens that way, then that would result in this way. So, it is behaving as if that. Now, whether that is true, right, this can be proved if we can characterize the output process from the first node, right. If it turns out the output process, if we can characterize, then this result is actually can be proved that this is true. It is not just a mere observation with respect to this particular system that you are talking about, but it is in general it has to be true, and why it is true is what you have to look at it. And Burke's theorem is what helps us to do this. This Burke did this work in 1956, that he gave this result for an output process of an MMC queue, and that is what we are going to see next in this lecture. Okay. So, what is the Burke's theorem which is characterizing the output process of an MMC system is what is the following. In an MMC queuing system in steady state, the inter-departure times are IID exponential with parameter lambda. In other words, what it says is that the output process is also a Poisson process with the same parameter as the input process. That is what it claims. Okay. So, let us see how this can be shown to be true, because the whole queuing network, in at least in our analysis of networks, that whatever we have been considering, like this output process plays a critical. So far we did not bother too much on the output process, but here it is very critical. So, it needs to be understood that how this is true. Okay. So, let us see how it can be proved. Suppose if you call n of t be the number in the system at time t, and T1 dash, T2 dash, Tn dash, Tn plus 1 dash denote the successive departure instance, so that if you define capital L to be Tn plus 1 dash minus Tn dash, then this is the interdeparture interval. Okay. Now, you define a function capital F suffix k of t to be the probability of this quantity. What is this? So, this is the joint probability that there are k in the system at time t after the last departure, right. The last departure happened at t and dash. Now, a time t has elapsed between the last departure and now, and you are seeing the system state. So, that is basically k, and this t is less than the interdeparture time, right. So, interdeparture time is more than, so this is what a typical L would be, right. So, L is greater than t, right. So, this t is less than the interdeparture, L is greater than t is what. So, then this is what is this probability Fk of t. Now, once we define this, then the CDF of L, right, because this is gives you L greater than t and n of something at equal to k. So, now if I want CDF of L, which is probability L less than or equal to t, right. So, if I sum over all possible k, then I will get this quantity as probability of L greater than t. Now, 1 minus of that would give me probability of L less than or equal to t. So, that is what will be the CDF. So, once I obtain this Fk of t, then from this expression I can obtain what is the distribution of this interdeparture time. Okay. Now, here since the input is a Poisson process, the probability that a departing customer leaves k in the system is equal to the probability that the number in the system is also equal to k, which means that the departure time probabilities will be equal to the arbitrary time probabilities, because here the system state moves by 1 and the Poisson process is what is the input process is. So, we therefore have at 0 Fk at 0, right, would be equal to Pk of the MMCQ. So, where this Pk is the equilibrium probabilities of an MMCQ, right, is what the initial condition here. Now, we can write down, if I look at for an infinitesimal interval of length delta t, I can write down the evolution equation to construct. So, I can consider that f naught in t plus delta t, okay, means that 0, remember Fk of t is the joint probability that there are k in the system at time t after the last departure, okay, and that this is t is less than the interdeparture time, right. So, which means no departure have happened by time t, that is what it would be, right. So, that is what we mean here, right, that this is less than the interdeparture time. The interdeparture time is after t is coming. So, between the last departure and up to now, there is no departure happened. That is what this gives. So, if that is the case, F0, its only way possibility is that again you are as usual, right, this interval 0 you are dividing into this interval 0 to t plus delta t, you are dividing into 0 to t and t to t plus delta t, and you are looking at in a small interval what is the probability and what would have been here, conditioning on that, right. That is what you are doing it. Recall the Poisson process or any Balthrud process or CTM like how we have obtained this particular set of equation. It is a similar process, that is what we are doing it. Okay. So, 0 here at t plus delta t could have happened in a way like there was 0 up to time t or at time t and no arrival have happened, right. No arrival would have happened. So, that things would have been here, right. Fk, now for k between 1 to c and for k greater than or equal to c, you will have two different things that you need to consider here. Okay. So, this is the usual way. So, this would be that no arrival and Fk, like up to time t it is Fk. Now, in between like no arrival, no departure. Now, the departure can happen at the rate k mu because k is between 1 and c, right. This is this term, or it could happen in k minus 1 and now one arrival could have happened and no departure would have happened. So, f k of t plus delta t, and this is similarly for k greater than or equal to c. Now, you by the usual process that you take this term this generic term f k of t to the other side, divide by delta t and let that limit delta t tends to 0, you obtain the difference equation which is given by this. Now, again this is more like your Poisson process case because f k minus 1 is what is involved in f k dash. Now, if I use the boundary condition which is f k 0 is p k is what we have observed, right. This p k is p k of MMC, and you solve in a similar manner as you do for a Poisson process, you will arrive at this expression where f k of t is nothing but p k into e to the power minus lambda t, right, where p k plus 1, you just recall the recursive relationship between p k plus 1 and p k for k between 1 and c and k greater than or equal to c would be expressed in this manner in the case of an MMC model. So, that part you recall, this is what this p k's are, this p k's are the p k's of MMC. Now, once I have this itself shows that this breaks it up into product of 2, but formally also you can plug it inside this f k of t and sum. So, you will obtain this. So, this is the distribution function of t. So, that means the inter-departure times are exponential with parameter lambda is what gives you this part. This is the first part. There are two more components to this, that the random variables n of L and L, where L is the duration, are independent and the inter-departure times are also independent. So, that is what we will see in the next two steps. So, this is the first step, that L follows exponential with parameter lambda. Now, again consider this portion, that what does this mean, that at n plus 1th departure instant, just after that it is equal to k, and right between t to t plus delta t there was a departure, right, or one service completion, right. So, that means that at time t this should have been in k plus 1 and one service completion in t to t plus delta t. That is what you are looking at it here, right. So, this is what is the probability. Now, this is what you are looking at it here, right. Now, this one service completion would depend on how many servers were busy, right. So, for k plus 1 less than or equal to c, k plus 1 servers would be busy and the rate of service is k plus 1 times mu, whether it is 1, 2, 3 and so on up to k plus up to c, like you will have this. So, while this rate will be c mu for k plus 1 if this is greater than c, right, that many were there in the system. If that is greater than c, then rate of service would be c mu because only c servers are in operation. Okay. Now, for this one service completion you put this rate expression. So, what you would get here, this f k plus 1 t you already know, it is p k plus 1 times e to the power minus lambda t, and one service completion for k plus 1 less than or equal to c, this will be k plus 1 times mu is the rate, and this is the probability of that one service completion. So, together this right hand side, this whole expression is what is the right hand side expression of for k less than or k plus 1 less than or equal to c. Similarly, just that k plus 1 be replaced by c mu, p k plus 1 and this quantity p k plus 1 times e to the power minus lambda t times c mu delta t plus order delta t would be the right hand side expression for k plus 1 greater than c. In both the cases, p k plus 1 if you write in terms of p k as we have seen here, right, you substitute for this one case, substitute for the other case, both will be reduced to this form, right, p k times lambda into e to the power minus lambda t times delta t order of delta t What that means is that this expression is equal to this. So, that means that this random variable and this random variable are independent, right. So, this is what is the first quantity is and this is what is the second quantity. So, these are all independent because they turn out to be distribution wise, they are written in this form. So, that means that those two random variables are independent. So, effectively what this means is that this L, which is the inter-departure time duration or the time for the inter-departure times L, and N of L, the number of in the system, right, in that intervals, right, or in that point at the time t, that is how we are defining it. They are independent, right. Now, we will use this to show the independence of the inter-departure times, because that is what we have to show. We have shown that it is exponential, but we have to show that they are independent as well. Then only it becomes exactly same as the Poisson process, the input process. Okay. Now, suppose capital lambda represents the set of a sequence or set of lengths of an arbitrary number of inter-departure intervals, right, subsequent to an initial interval of length L. So, you consider an initial interval of length L, then you consider the remaining ones, which is basically a sequence. It could be any number of departure can happen, could have happened during that period, or you take suppose 5 departure length or 6 departure lengths and so on. So, that is what this capital lambda represents. Now, the Markov property implies that this one probability of this length given the number at the beginning of that sequence, right. Remember, there is a initial length of L and further there is a length of capital lambda in which an arbitrary number of departures have happened. So, this is the sum of an arbitrary number of inter-departure intervals. Okay. Now, this length and what was the number in the system at this point, they are independent because that is what is Markov property. So, that means that probability of this capital lambda given N of L is same as probability of capital lambda given N of L and L. Whatever be that length also is not going to play a role into the future, right. And since we already shown that just that N of L and L are independent, for this purpose only we needed that, because N of L and L are independent. So, that means this joint probability is the product of the individual probabilities, right, whatever be this quantities. Now, if I consider the joint probability function of the initial interval length L at the end of the interval, which is N of L, and the capital lambda, which is the set of subsequent interval lengths. Okay. If I consider the joint probability of this, I can just simply use my conditional probability argument to write this joint probability as probability of capital lambda given N of L comma L and probability of N of L and L. Now, from this property, this quantity is nothing but probability of capital lambda given N of L, right, the first probability. The second one, because of these two are independent, so this is nothing but the product of these two. Now, I can write this combinedly as probability of capital lambda and N of L multiplied by probability of L, right. Now, if I sum over all possible values for this NL, which is 0 to infinity, if I sum over this, what I will get is this expression. What this shows is that probability of L and lambda, capital lambda, is equal to probability of L into probability of lambda. So, this proves the mutual independence of all the intervals. This is what is the Burke's theorem. Basically, what we need is the main idea that what is the output process in an MMC system. So, what the example that we have considered, it is a 2 node series network, is basically MM1 system we have considered for simplicity, though it is also true for MM1 system. So, the output process, right, remember here we are not doing anything here, like all arrivals go through the system once and then they leaves, they do not come back or no such thing is happening. In the normal MM1 system, MMC system, the output process is also a Poisson process with the same rate as the input process. That is what, but this is a very useful powerful result in the context of our queuing network. Okay. So, that is the reason why in the 2 node network the result came out to be the product form of the distributions itself, not just the product form solution, it is the distribution itself came out to be product form. So, now we consider we move on to general queuing network. After having seen certain ideas about an open network, closed network, mixed network, and what are the additional specifications that we need to give to describe a particular queuing network in general settings, right. We move on to the study of queuing networks in the context, but we restrict our study not just to any general network, but with certain conditions. Okay. So, what we consider, the system is consisting of a network of queues with k nodes in general. Okay. So, some number of nodes, some finite number of nodes. So, we consider k nodes are there in the queuing system. Now, each node represents a service facility with Ci server. So, node I has Ci number of servers, and there is an infinite capacity queuing component in front of each of this node or station, whatever we want to call it. So, it means that they are assumed to have infinite buffers in front of each of this service facility or in each of this node. In general, customers enter the system at any node, they can enter in any node and traverse from node to node and depart from any node. So, and all the customers need not traverse through all the nodes, or all the customers need not follow the same path, right. Every customer has a path before he exits the system. Okay. And in the process there may be feedback, meaning that a customer may return to a node in which he has already received the service. Okay. It can happen in a production system, right. So, you pass through certain things, like you go to the next stage, that is something is done, then some defective happened, then you have to start all over again. So, you will come back to this. It is possible that feedbacks are there, but if it is in some situation, feedback will not be there, because if it is passing through, a packet is being passing through the network to outside, then it will not be coming back to itself generally, right. But it can be, but it is a different matter, but it may not be also. So, you may require that also. So, a feedback possible, or simply it is a feed forward nature of thing, and also it need not visit all nodes too. So, the main characteristics of our network that we are going to consider are these 3 points, where what we assume is that arrivals from outside this network of queues to this queuing network follow a Poisson process at each of these nodes, wherever the arrivals happen. It need not be that at all nodes there could be arrivals. Okay. Like the 2 node example that we have seen, that only in the node 1 there have been external arrivals, in node 2 there was no external arrivals, right, and there was no feedback, it was just feed forward. After finishing in node 1, it went to node 2, and from node 2 it exited. From node 1 there was no exit, right. So, it's all these things are possible even with that simple setup. Okay. So, arrivals from outside to node I or station I follow a Poisson process with rate gamma I. Okay. Service or the holding times at each channel at node I are IID exponential mu I. Now, this mu I can depend on the queue length. Okay. And the probability that a customer who has completed service at node I will go next to node J, which is what is called as routing probability, is Rij, okay, where I from 1 to k, j from 0 to k, that 0 means Ri0 you will get. That Ri0 indicates that the probability that a customer is leaving from node I with that probability. That is what this Ri0 will give you. So, there is one mode index. So, basically there is k nodes 1 to k, you name it inside the system. There is outside node, which is what you call it as departure, you call that as node 0 and you denote it with the corresponding probabilities from each node as Ri0. Okay. The probability that will leave the system from node I is Ri0. Okay. The networks with all the above properties are what are called as Jackson networks, which is was considered by Jackson in 1957 and 63 and so on. They will have product form solution in the true sense. It may not be that product form in terms of distribution functions, but the solution would be in product form. We already mentioned about what that would mean. We will come back to that again when we actually see it. Okay. So, if I have to draw a typical network, suppose if I call this as some node 1, say there are C1 servers and it's each of them with rate mu 1, and there is some node 2. Okay. So, this is there are C2 and node 2, and there is a node 3 with C3 and mu 3 as its parameters, means C3 servers each with rate mu 3, that is what we have. And then and so on you will have, and then you will have Ck mu k is what is the last node or the kth node that you may have. Okay. So, the subscripts will tell you which node it is. So, the arrivals, the external arrivals, if I draw it, so the external arrivals to each of these nodes is at the rate gamma 1, and here it could be gamma 2, and here there may not be any, and here it could be gamma k, right. After finishing this, right, after finishing service at here, so from this node it will move to node 2 with probability R1 2, and it will move to probability this with R1 3, and so on. It can move to this with probability R1 k. So, this can happen, okay. And from node 2, right, it can move to this one with R2 3, and so on. It can go here with R2 k, or it can even come here with R2 1. Okay. And from here, suppose it need not that from everywhere there needs to be passage or movement to every other node. Okay. So, from here, for example, it can go only here, for example. So, this could be R3 2, and from here if it goes out. So, now if I depict the things going out, so this probability is R1 0, this probability is R3 0, and this probability is RK 0, and so on. Okay. And possibly from here also it can come to here with probability RK 1. So, you could have a general setup here. Okay. So, this is what a typical general open queuing network will be there, because this is open, because we see that there are external arrivals at least in one node, and there is departure from at least in one node. So, here you see arrivals happening in node 1, node 2, but not in node 3, but in node k. Departure happens from node 1, node 3 and node k, but not from node 2, can happen, right. So, this is how it will behave, right. So, this is that is what we said, how they are interconnected, what is the routing probabilities and the blocking, if there is one, we have to specify. These are the additional characteristics that we need to specify for a queuing network. So, this is how typically it will look like, and that is what we have basically described here. So, there are CA servers at node I, enter from any node, traverse from node to node in any manner, that we have to specify, because it is not that it decides, but from which node to which node it will go, at with what probability it will go, we have to specify, and depart from any node, possibilities we are thinking about, right. There may be feedback or only feed forward, and need not visit all nodes. Arrivals from Poisson with rate gamma I, service times are exponential with mu I. Rij will give you the routing probability, which is independent of the state of the system. That is also an important point here, which you note, that Rij need to be independent of the state. Without that, it will pass, right? It depends on the state of the system, either in I or J or origin and destination, that will happen, okay. And Ri0 is the probability that the customer will leave the system from node I, that is what will happen, right. So, and we assume that all of these queues have infinite capacity. If they have finite capacity, then blocking issue comes, which we will deal later, okay. This is what in general the setup, right. So, this is what a typical queuing network behavior would be, right. So, the quantities here gamma i's, Rij's, Ci's, mu i's and so on, right. This is what is the parameters for this queuing network. Like in general, it is very difficult to depict in a multi-network case, but at least with few nodes you can always decide. Now, you see that the earlier 2 series 2 node 1 is a very special case of such general network. So, this is what is typically called as Jackson network with the assumption of Poisson arrival, exponential service times, infinite capacity and so on, is what is called as the Jackson network, okay. Now, networks where gamma I equal to 0 and Ri0 equal to 0, right. So, there will be no this red color links or the purple color links there in this, okay. They are referred to as closed Jackson network. They are referred to as closed Jackson network. In the general case that we have considered is open Jackson network, because there are external arrivals, there is departure to outside world, okay. So, that is what they call open Jackson network, okay. The finite source queue that we have seen as a special case of a BDP queuing system, which is basically the machine repairment problem, you can think of that as a closed network. It is a closed queuing network with 2 nodes, one representing the operating machines and the other is the repair facility. The totally M machines, between totally there are M customers. They circulate between these 2 nodes and these 2 nodes, either in operating condition or in the repair facility if they have failed down, okay. So, 1 represents the operating node and 2 represent failed machines, and the routing probabilities here is 1 to 2 is 1 and 2 to 1 is 1, okay. If there are imperfect repairs happen, suppose in the same scenario, meaning that you repair once and finally you found out that there is still an imperfect repair, one would call it is additional feature, repair means it is not completely repaired. One could have a scenario where there can have been imperfect repairs, then it has to go to repair again, then there could be a feedback to that, okay. We are not considering that is generic one, what we have seen so far, that it is basically even with imperfect repair, it can be still considered as a closed queuing network, okay. But it cannot be then part of this BDP business, right. So, and all other Rij's are 0 is what then you have here. So, this is a closed network, we already seen one example of closed network of this nature, okay. But we will start our discussion with open networks where gamma I we assume to be lambda for I is equal to 1 and Rij, which is the routing probabilities, okay. This routing probability is 1 when j is I plus 1, right, after finishing. So, it enters in node 1 with the rate lambda and there is no arrivals happen in any of the other node. So, the arrivals comes in the first node and movement, right, if j is I plus 1 for I between 1 to k minus 1, it is 1, which means from node 1 it enters in node 1, it then goes to node 2 with this routing probability and node 3, node 4, node 5 and so on all the way up to k, and when I is equal to k and j is equal to 0, it is 1. So, which means and it departs from the kth node. So, it is just that a series network with k nodes, what we have seen earlier 2 node, now it is generalized to k node. So, these are called series or tandem queues where the customer may enter from outside only at node 1 and depart from node only from node k. Once we study this, then we generalize to from series to a general open network of this type. So, this figure or this type you remember it because we might coming back to this figure right? You will not come back, but you just remember that this is what a general open network would mean here, okay. And then to closed junction network. So, we are considering here only Markovian queuing networks, we are not considering even general service time or anything of that, then things become much more complex. Anyway, one can look at if you are interested further, but our study or our analysis would confine to only Markovian system, where the exogenous inputs are Poisson, holding times are exponential, routing probabilities are known and state independent. That is a scenario that we have in mind, okay. So, this is what is a series. So, basically series or tandem queuing network, basically this is a series of service stations through which each calling unit or each customer must progress prior to leaving the system, which is typical in many manufacturing processes, assembly line processes, clinical systems, computer networks, communication networks, when the packets are being sent, possible. Computer communication at least is more general junction network come, but you have a specific sequence, it goes through only that sequence, mainly in manufacturing and clinical systems and hospitals basically, right, you would see here. So, it is basically what you have, this is the depiction that you have here, that there is a node 1 to which our external arrivals happen with rate lambda, C1 servers at node 1 with rate mu 1, and after completing service at node 1, it moves to node 2, which again has an infinite queuing capacity. All of these queuing capacities is infinite, which has C2 server each with rate mu 2, after that node 3 and so on all the way up to kth node, okay. And we do not have a no restriction capacity in the waiting room between the stations, that is what you have here. Now, from the knowledge that we have gained from our discussion of this 2 node network that we have seen already, right, we see that each of these station, there what we said, analyze that 2 node, it actually you can treat each node separately as an independent entity, and for the whole system then you have the complete picture in hand. That is what you have seen, that is also true here, right. So, each station can be analyzed separately as a single stage queuing model, and because of Burke's theorem, all the stations are independent MMC models as long as there is ample holding spaces in front of each node, because nothing is happening that you are not able to get into this queue, not really into the service, but into the queue. As long as that is there, each of them, because Burke's theorem says that what? So, this is input to the Poisson. So, the output is also Poisson, and hence input to the second queue is Poisson with the same rate as lambda. So, this is again is an MMC model, this is again an MMC model, each of these nodes are MMC model. So, you study each node separately, which you already done it with the MMC model, right. So, the whole system study, which means what you are looking for, the joint distribution of the number of customers or number of calling units or number of jobs in the network, which means that at each station how many are there is given by product of the marginals, right. That is what is the advantage when you use the Burke's theorem. You see that all stations are or all nodes are independent MMCI models. Okay. Thus, the MMC results can be used, okay, on each node individually and a complete analysis of this series or tandem queuing network. Series or tandem is interchangeably used, the word both mean the same, okay, tandem queuing network is possible. So, if I denote this as my steady state probability that there are ni customers in the ith node, then this quantity is given by now the product of the marginals, right, where this P n I is the probability that there are ni customers in an MMCI queue in steady state, of course, under the condition that rho I equal to the lambda by C I mu I times is less than 1. Okay. So, this is in a product form result, it falls into that category. We just said that product form means this joint probability can be written as some constant times product of function of ni's. But here it turns out that even the distribution itself comes out to be in that way. So, it is really product form probable solutions, meaning the independence. Okay. So, this holds good in a more general case of Jackson network too, as we are going to see little later. Now, it is possible to carry out analysis of this kind of series network as long as you you have the finite queue only in the last stage, because even up to that what will happen, then the input to the last stage is also Poisson, then the last stage alone is a MMCK model kind of thing, right. But if there is in between, things become complex, but this exact same result, right, then what will happen, the last one alone would be the corresponding results of an MMCK model, that is what will happen. So, this exact same analysis can also be utilized or holds or see that okay, this is true if only the last node can have the capacity limitations, okay. But there with blocked customers should be dropped from the system, right. When in the last node is full, then the customers are dropped from the system. With that understanding, the same idea can be utilized and you can still have the product form solution in that case. But beyond that, expanding in the series type itself is complex. And the analysis of feed forward networks, right, meaning that the networks in which customers are not allowed to visit their previously visited nodes is quite similar to the series networks. That is because of the property of the output process that you have. As long as there is no feedback, you look at here that each total output process is lambda, okay. But the output from here, right, if this is the rate, if you are looking at it, it is lambda times R10 is what is the rate of departure from this node, and this will give you rate of input to node 3 and so on, okay. This is true, but the moment you have this business, so which is coming from one of the visit, so it comes here, right. It may so happen that this particular customer has gone through stage 1, stage 3 and here it comes to only state 2. So, for example, he comes here state 1 and then state 2 and from state 1 again it comes to state 1. So, as long as there is a feedback, in the literature it can be shown, it is available in the literature and it can be shown that the input, the total input then is not really a Poisson, okay. But as long as there is no feedback, it is only feed forward network, then this branching, each branch is Poisson and hence the net input in that particular node will also be a Poisson, and hence this can be analyzed in a similar way as a series network. That is possible as long as you have only a feed forward network, okay. But the moment there is a feedback is there, the independence will be lost because of this dependence. It is not really the Poisson input that you are going to see anyway. So, that we will not prove the reason why the analysis with feedback networks becomes difficult here. But we are not going to consider this, but anyway it will be in a similar light. It is not very complex if you have only feed forward networks, of course, okay. Let us take a simple example to see like what the series network did. Suppose there is a supermarket, customers come, there is ample space for any number of customers to come and do their shopping, and once they finish the shopping, they just do not wait in front of the checkout counters, but there is a common lounge in which they wait with their carts full, whatever they shopped until that point of time. And if any checkout counter becomes free, then they will go to that checkout counter. So, from the lounge also like they will go in the order of their arrival. So now customers arrive according to a Poisson process with rate of 40 customers per hour, and the shopping times are on an average is exponentially distributed with the mean of 45 minutes, and the checkout times is basically 4 minutes on an average, again it is exponentially distributed. The question is, what should be the minimum number of checkout counters needed for the system to be stable? 1. 2. If we add one more checkout counter to the minimum number of checkout counters given by this requirement, then what is the average waiting time in the lounge, which means you can think lounge as a common queue from where the individual individual servers are drawing customers for service, okay. So, what is the average waiting time in lounge and how many customers on an average will be there in the lounge, which means in the common queue, how many people on average will be there in the entire supermarket, means those who are still shopping and those who are waiting for checkout. What is the total number? What is the average number? Right. Now you can see, since the first node is basically a self-service system, because there is no fixed number of servers here. Everyone, the moment you come in, you can start your service, which means the shopping. Then it is an infinity system, right. So the first stage is an infinity system, right, with rate lambda 40 and mu is 4/3. Second stage is an MMC, because the number of checking counters is there. Because of the Burke's theorem, it also has an input lambda 40 and mu is equal to 15, okay, and we were to determine what is the minimum number of C that is required. Now we know second stage is MMC, so for the steady state to exist, we need lambda by C mu is less than 1, or C mu is greater than lambda, or C is greater than lambda by mu. Lambda by mu, it turns out to be 2.67. And hence, right, this is turning out to be C must be at least 3. So, there must be at least 3 checkout counters is required for the system to be stable. That means the minimum number of checkout counters needed is 3. Now, our second question is that if we add one more count to the minimum, suppose if we add now one more to make it 4 counters, then the node 2 is now MM4 system. Now, from the results of MMC, the P naught you can compute to be approximately equal to 0.06, and WQ is 1.14 minutes and LQ is 0.76. These are nice numbers, very good, because the number in the system in the which means the common queue, how many customers are waiting, is just less than one customer waiting on an average. And even if someone waits, the average waiting time is just 1 minute. It's a very good thing if you want to have. Okay. Now, if you want to see what the total number of customers in the whole supermarket, right. So, that will be L, which is be sum of L of this node 1, those who are shopping, plus L of those people who are the checkout counters, L of this MM4. So, this is basically L of MM infinity is lambda by mu, and L of MM4 is exactly this quantity. Now, if you simplify, it is 33. So, there are 33 people who are there in the supermarket at any point of time. Probably this might help to determine like how many carts you keep and where you will keep and so on, right. So, that is the reason why you wanted to do that, for or any other reason, does not matter, whatever is the case, right. That is what you are seeing it here. Now, you can do a similar analysis, similar calculation with C is equal to 3, and to see how the congestion is getting increased, or what is the impact of this additional one, how much this has made the life easier for the customer and so on, right. So, this is a series network. So, basically what you have seen is that very simple network and how it can give you some insights about how the system operates if you have to model such kind of things. Okay. So, this is about the series network. Later on then we will generalize to a more general network in the following lectures. Okay. Thank you. Bye.